this example is another sort of a classic type of problem that you typically see in calculus books, and they have real applications. A conical tank with a vertex down is 10 feet across the top and 12 feet deep. If the water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. Well, what I need to do is draw a picture. First of all, a conical tank looks like this. And I know that it's 10 feet across the top, so from here to here is 10 feet. And it's 12 feet deep, so from here to here is 12. Think of this as my ground right there. And let's see, I want to find the rate of change when water is 8 feet deep. So at some point, I'm going to have this as being 8. This is some radius. And this is some other radius. And actually, this other radius, I know what this is. This is 5. Now, this 8 is actually h. And h is changing as the water is pouring in. And the water is flowing into the tank at a rate of 10 cubic feet per minute. So what this has given me is dV, the rate of change in volume, with respect to time, equals 10 cubic feet per minute. And what this is asking for, the rate of change in the depth of the water. Well, if I call this h, if I call the depth h, the height of the, or where I am, the reference to the height of the cone, is asking for dh dt. So I know I will be taking a derivative here with respect to t. So I have v equals this. So dv dt will be equal to, you know what, before I do that, because I have a product rule right here, I think I'm going to work on this just a little bit more, see if I can't get rid of this product rule to make it a little bit easier to take the derivative. So I'm going to look for relationship here, and I know that this is a right triangle, this is a right triangle, so these are similar triangles. So when I look at this, I know that r is to h. At some point I'm going to be 8, but h is changing and r is changing. These are both changing. So no matter where I am, if I'm down here, if I'm up here, this is always a right triangle. And I know that this radius r in relationship to h, r over h, will be proportional to 5 over 12. I know that this is always going to be equal to each other. And what I want to do is I want to say simply that this is then going to imply that r is equal to 5h over 12. So what I did is I wrote r in terms of h. Well, by doing that, I'm going to come back into this, and I'm going to say that volume is then equal to pi. R squared is 5h over 12 squared times h over 3. So I could simplify this a little bit. This would be, the 5 would be 25, the 12 is 144. So 25 over 144 pi h cubed over all over 3. So when I take the derivative with respect to time, this is what I want to take the derivative of, because now it only has one variable h. And I need dh dt. That's why I solved r for h and not the other way around. If I would have solved h in terms of r, I would have ended up with a function that involved just r, because h would become a function of r. But I need dh dt. And when I take the implicit differentiation, I'm not going to end up with a dh dt. Now I will. So dv dt equals the derivative of this. I'm going to keep all those constants out front here. I could and probably should multiply this 144 by 3, but I'm going to leave it for right now. Pi, oh, I'm glad I left it, because now I'll have 3h squared dh dt, so now the 3 is going to cancel. So I guess it was good in a way that I was lazy and didn't multiply that out because it went away from me nicely. So dv dt, which by the way we said was 10. So 10 cubic feet per minute is equal to 25 pi over 144 h squared dh dt. So what I want to do now is I want to solve for dh dt. That means that, see, 10, and I'm going to keep all my units with me this time, cubic feet per minute, and this would be multiplied by 144, and then divided by 25 pi h squared is equal to dh dt. Now it wants to know the rate of change when the water is 8 feet deep. Well, that means h is 8 feet. So when that occurs, let me erase just a little bit of this to give myself a little bit more room here. Okay, now I got a little bit more room to work here. So I'm going to have dh dt, the rate of change of height with respect to time, is going to be equal to 144 times 10. That's 1440. I will have cubic feet per minute divided by 25 pi, and h is 8, but 8 feet squared. So the feet squared will cancel with the feet cubed to give me just simply feet. And then 8 squared is 64, so I'm going to end up with 1440 over 25 times 64 pi, and the units that remained are feet per minute. And that actually makes a lot of sense because the height would be in feet, not squared feet or cubic feet. The height would in fact be in feet, and that's the units that I ended up with. Now if we want to simplify this out a little bit more, I'll do it a little bit over here. This would be 1440 over, see, 25 times 64 gave me 1600 pi. These zeros will cancel. Of course, I'm still at feet per minute. So I guess I could leave this at, well, I could reduce it farther. I'll let you mess around with that. If you wanted an approximation, then if you put this in a calculator, you're going to end up with 0.2865 feet per minute. So when we put it in this form, actually this approximation probably has more meaning because you can see that this is slightly more than 1/4 of a foot per minute, and that when you put it in those terms, you can kind of picture it. 1/4 of a foot per minute, that's about 3 inches per minute ish, because this isn't exactly 1/4. So when I'm dumping water in at 10 cubic feet per minute, and I'm actually at this point where I'm at a height of 8, at that instant it's rising at a rate of roughly, not a little bit more than 3 inches per minute. Now the interesting thing for you to think about, and you should probably ask about, because I'm not going to give you the answer right here, you could calculate very quickly. Do you think that the rate of increase in height would be greater if I was down here someplace, or less than right here at 8? And if I was up here someplace, do you think the rate of change in height would be greater than or less than what it is at 8? And that'd be easy calculation to do to confirm, because all you need to do is come back in for h and put in some new height, less than 8 and bigger than height. But just intuitively, just think about that, because the rate of change is constantly changing itself. Do you think it'd be greater down here or less than? And up here, do you think it'd be greater than or less than our comparison at 8?